Let's practice using our constant acceleration equations. This is when your equation card becomes even more important, because in the notes you were given several equations that help define what a term was, like acceleration A equals delta V over t, and velocity equals distance over time. And I have found that if you guys write those on your cards, or if you keep those in your head, you will misuse them. Because the velocity equals distance over time, you can only use it if there's no acceleration. So instead, if you use the three equations I've given you, they will correct for all of those situations on their own. So those equations, V equals V naught, and that's how we call that, means initial, plus A times T. X equals X naught plus V naught T plus 1/2 AT squared. Now I write these equations every time I use them, so I have them memorized just because of that. And the last one, V squared equals V naught squared plus 2A X minus X naught. We're going to use these equations more than any other equations in all of physics. In fact, the first two we will use all the time. We'll use the third one occasionally when we don't know time and we don't want to solve time. Usually if we have to use the third one, we could get there using like the first and then the second. So there's oftentimes more than one path, but these three equations need to be your physics Bible, basically. So let's do a practice problem. A soccer ball rolls up a hill. Assume that the direction up is the positive direction. I won't usually tell you which way we're going to say be positive. You can make that decision. As long as you're consistent, it doesn't matter. So we're going to start by writing down what we know. In the first part of the question we have, if the soccer ball starts with a velocity of 2.5 meters per second, so we know that that's the initial velocity, and because it's positive, that means it's rolling up the hill, and slows down at a rate of negative 0.50 meters per second squared. Now, slowing down and speeding up is acceleration. So this is our acceleration, and if you weren't sure, you should have been able to look at the units and tell. Now because this is negative, it doesn't automatically mean that it would be slowing down. It's just the acceleration is in the negative direction. And because the initial velocity is positive and the acceleration is negative, they're opposite signs, that means we're slowing down. You're asked, what is the velocity after 2 seconds? Time 2.0 seconds, and I find that if you write the variable you're looking for, then it makes it very easy to pick out an equation. Because if we look at all these variables we have and need, we see that this first equation right here is the one we're going to need to use. And like I said, I always write my equations because it helps me remember them. You have a equation card, so you don't have to memorize them, but if you know them off the top of your head, it makes things quicker and easier for most students. So velocity equals 0.5 meters per second plus meters per second squared times 2 seconds. Now you can see that this second cancels out that one, so we have meters per second plus meters per second. So we get 2.5 meters per second plus -1 meters per second. And so we've got that our velocity after 2 seconds, is 2.5 minus 1, is 1.5 meters per second. And we can put our positive sign to indicate that it's still uphill. We should double check our significant figures. We have 2 and 2 and 2, so our answer should have 2. So this is our answer for the first part. second one is, what is the soccer ball's velocity if the constant acceleration continues for 6 seconds? So it's saying if we had this same acceleration, what if instead of 2 seconds, we had t equals 6 seconds? So we use the exact same equation. I know that when you show your work, you might not have to show me the algebra because you can do algebra. You don't have to show me this step, but you do have to show me this step, and you do have to show me this step. Otherwise, I can't see how you're doing your math. I need to see that you plugged in everything correctly and that you did the calculations correctly. This listing of what you know really helps me as well because sometimes you misunderstand what a variable is, and that's your problem. And that way I know if it's misunderstanding a variable or not using the correct equation. So for the second one, we've got the velocity equals 2.5 meters per second plus negative 0.5 meters per second squared times 6 seconds. And this time I'm not going to show out all the algebra. I'm just going to put an answer. So we get 2.5 minus 3. So we get that our velocity is negative 0.50 meters per second. Remember that we need two significant figures. So because it's negative, that means it's actually started rolling down the hill. Let's do another practice problem. So we have a bike traveling at a constant speed of 4 meters per second for 4 seconds. How far does it go? So always start by writing down what you know. Velocity is 4 meters per second. And it's a constant speed. That means this is the final velocity, the initial velocity, and every velocity in between because acceleration equals 0. We know that time is 4 seconds. And I've told you that unless it specifically tells you otherwise, the initial displacement can always be 0. And we want to know how far it goes. So if we look up at our equations, we can see that the second equation will help us solve for this. It says v0, but we know that this is v and v0. There is no final velocity, it's always the same. So our equation is x equals x naught plus v naught t plus 1/2 at squared. So x equals 0 plus velocity times time plus, and because acceleration is 0, all of that's 0, you don't have to plug in. Seconds cancel out, and we get 16 meters. And if we look at significant figures, we have 2 and 2, so we have 2 in our answer. Okay, in this example, we've got a car accelerating at a constant rate. That just means acceleration doesn't change. We don't deal with any problems with changing acceleration. So from 15 meters per second to 30 meters per second. So we have our v initial, our v naught, and our final velocity. And it travels a distance of 125 meters. That means the initial displacement is 0 and the final displacement is 125 meters. In fact, we could make the initial displacement be 100 and the final be 225. It just needs to be a difference of 125. You might notice that when I list my variables here, I always write them exactly like they are in the problem for their significant figure reasons, but when I put them in the problem, I can drop those extra zeros if I don't want them. And we're asked to find acceleration. So I added the equations to the top. So for this one, if we look at our variables, we can't use this one because we don't know a or t. we can't use this one because we don't know A or T. So we have to use this one. It's the only one that can give us acceleration if we don't know time. So v squared, v naught squared, and if we plug in, we have 30 meters per second squared, 15 meters per second squared, to A, so 125 minus 0 meters. So if we do our math, and I'm going to show the steps here because we don't use this equation as frequently. So for this one, you do 125 minus 0 is for this one you do 125 minus 0 is 125. And we can go ahead and multiply by 2. So we have 250A. Now we're going to combine like terms. Because it's addition over here, we're going to subtract 225 from both sides. And you get 675 meters squared second squared equals, I accidentally left that off, I'm sorry, 250 meters times A, and the meters up here. Now to solve for A, you divide both sides by 250 meters. And when you divide this side by 250 meters, that cancels out one of those, giving you meters per second squared, which is correct for acceleration. And let's think about significant figures. We have 2, 3, and 3. So we're going to round our answer to 2. And we get 2.7 meters per second squared. The most common mistake with using this equation is that people don't subtract to combine like terms. We're so used to doing multiplication and division when we move things around that sometimes we trick ourselves. Let's do one more practice problem. This one seems to not have very much information, but there is some implicit information that you might not notice. The dragster starting from rest. That's important. That means the initial velocity is 0. And it has an acceleration of 49 meters per second squared. And it wants to know how fast is it going when it has traveled 325 meters. And we want to know final velocity. And then later we want to know how long does it take. If you look at your equations, there's two ways to go about this. Given what we already have, we could use the third equation to solve for velocity. And then we could solve for time using either of the other two equations. Or we can use the second equation to solve for time, and then the first equation to solve for velocity. Most people don't like using that third equation unless they have to. So I'm going to show finding time first and then finding how fast. You don't have to solve problems in the order they're asked. A lot of times if you solve for time first, it'll help you out, especially if you're asked to solve for time anyway. Then it makes sense to do what you're more comfortable with. So And again, if you choose to use that third equation, you are welcome to it. It's not incorrect. There are often more than one paths to the correct answer in physics. So 325 meters. And this one's 0, and this one's 0. And so if we simplify this, and again, you don't have to show this step, but I'm going to. We can drop all those zeros and say 24, 5. And then we divide both sides. And I'm not going to do that math right now because I have to round then. But that gives us something like 13.265 equals t squared. And then we have to take the square root of both sides to get t. So always remember that the less rounding you can do, the more accurate your answer will be. And when we're talking about significant figures, we've got 2 and we've got 3. So we're going to round our answer to 3.6 seconds. And that's our answer here for the second question. Now we can use this and the first equation to solve for the final velocity. And that cancels out there. And this also is going to have 2 significant figures. So we get, it starts out as 176 and we round that to 180 meters per second. Please do some of the practice problems and let me know if you have questions about this. This is a foundation. We're going to build on this. We're going to make it harder and start doing things that are moving in 2 directions at the same time, both maybe forwards and up. So in 2 different dimensions at the same time. So if you don't understand this part, it's going to make the next part really, really hard. So please ask if you need help.